Hi there, Mr. Sutton here with the AB Calculus 5.5 Extra Practice Number 1 Solutions on RAM Part 2. For this problem, we're trying to pick the integral down here that's the limit of this Riemann sum. So there's a lot of things to consider here, but we're eventually trying to put this in the integral from a to b of f of x dx kind of format. So I need to figure out my limits of integration because we've got some different options here, and also what function we're dealing with. So the key on this one, this 3 over n, this is your differential. And because we have a 3 divided by n, that means that the interval length is going to be 3. You're basically dividing 3 into an infinite number of pieces because n is approaching infinity. And you're just getting rectangles that you're adding together with all these infinite pieces. So we don't know what a and b are, but we know that they're 3 apart. So once we figure out a, we can add 3 to it and get b. So getting a is the next tricky part. So a is possibly this plus 2, possibly not. It's kind of hard to tell just by looking at this if this is like an x squared situation and a is 2, or if this is an x plus 2 situation with an a value of 1. In order to figure out which it is, if you take a k value of 0 and plug that in here, that'll essentially tell you what x value you're starting at when you start adding up all these rectangles. So if I take the k value 0, I essentially have 0 plus 2, which means that I really am starting with an a value of 2. Therefore, if I add 3 to that, I'm going to get my b value of 5. Now, another way of finding the b value is you could take a k value of n and plug that in, and then if you have 3n over n, well, that's just 3. Plus 2 gives us 5. So just another way of getting the same answer. So the fact that a is 2, the fact that this plus 2 is the a value, means that this whole expression in here is really just one big x that's being squared. So then we're going to end up with the integral from 2 to 5 of x squared dx, and that's going to end up being choice C. On this problem, I'm trying to take this integral and convert it into a Riemann sum kind of form. So I'm basically trying to get the form limit as n approaches infinity of the sum from 1 to n of f of xk delta x. So I'm essentially trying to pick out, what am I plugging into my cubing function, which is what's going on here, and what is my delta x going to be. Delta x is the easiest part to pick out, and it actually determines what goes inside your function. So in general, delta x, that's going to be your interval length divided by n. And the interval length in this case, b minus a, is really 5 minus 1. So this is going to be 4 over n. Next, to get this kth term, this kth x value, you're taking your starting x value, which is the lower limit of integration, a, and adding k times the delta x. So this is going to be 1 plus k times this 4 over n that we just found. And now this whole thing is going inside your function. So when I write all this out, I'm going to have limit sum of, and then we're going to have 1 plus 4k over n cubed times our delta x of 4 over n. Looking at my answer choices, it looks like that's going to be choice C. They're all pretty close, but you'll notice that choice A didn't have a 4k, and choice B, we were missing the 4 over the n there. And D was just wrong for both of those reasons. On this problem, we're trying to pick the Riemann sum, whose limit is this integral. So we're basically converting this into this form here. So we need to pick out the xk and the delta x, and then we're going to do sine of 3 times that, essentially. So let's start with the delta x. That's always the easiest thing to pick out if you're starting with the definite integral. So that's going to be your interval length, b minus a, over n. So in this case, b minus a is really pi minus 0, which is just pi. So we've got pi over n then for the delta x. And for my kth x value, that's a plus k times the delta x. So that's going to be an a value of 0, lower limit of integration, plus k times the pi over n that we just had here. So this is just going to end up being k pi over n, or pi k, either way, plus 0, but we don't have to write the plus 0. So this pi k over n, that's what's actually getting plugged into this sine function here. So I'm going to have sine of 3 times pi k over n for this f of x k. For the delta x, we've just got pi over n. So all of this stuff here. And then you'll notice that that doesn't match any of the answer choices because they actually multiplied the stuff in here out. So we can actually write this as 3 pi k over n, and then everything else is going to be the same. So looking at my answer choices, the only one that has a 3 pi k over n and a pi over n is choice D. For this problem, we're trying to pick the integral that's the limit of this Riemann sum. So before I start trying to pick out a values and b values and all that, I noticed that this 3 over n, which is my dx, isn't quite represented clearly inside the function. I've got 6 times k over n, which is kind of close, but it's not really like having 3k over n. So I'm going to rewrite this by taking a 2 out of this second term in here and rewriting it as follows. So everything else is essentially the same. The only thing I've changed is instead of writing 6k over n, I'm now thinking about this as being 2 times 3k over n. Okay, so at this point, we're trying to convert this into integral from a to b of f of x dx form. The dx is already kind of accounted for with this 3 over n, but now we have to get the a, the b, and that'll help us figure out what the f of x is. So looking in here, it's kind of hard to pick out the a value from this because we've got this little plus 1 in here, which makes me think, well, maybe 1 is the lower limit of integration. And certainly we've got answer choices like a and c where 1 is the lower limit of integration. So how can we tell if this 1 is a lower limit of integration or just part of the function like in choices b and d? The key on this one is to take a look at how this xk term evolves, because that's really what determines what your function looks like. The xk term, that's essentially the a value plus your k delta x. Well, here's delta x, here's k delta x. What is being added to k delta x before the regular function starts doing stuff to it? Well, nothing. It's getting multiplied by 2 before this 1 is being added. That means that stuff is happening to k delta x before this 1 even enters the picture. That suggests that we have an invisible 0 being added to k delta x in here, which means you would have an a value of 0. So if that is the case, then that means our b value is going to be 0 plus this 3 here, which means we have a b value of 3. And let's see if we can get all this to match up with one of our functions. So we've essentially got 0 plus k delta x in here. That's being multiplied by 2, so you can think of that as like 2x, and we're adding 1 to it, so 2x plus 1, all of that inside a sine function. So when the dust settles, we can write this as integral from 0 to 3 of sine of 2x plus 1 dx, which is choice B. For this problem, I've got this Riemann sum expression here, and I want to figure out how to convert it into integral form. So the first thing I'm going to look at is my delta x, this 1 over n right here. It's always going to be your interval length divided by n. And I'm now going to look inside here to see if I can pick out where my delta x is, because I want to find k delta x in here. Knowing k delta x, that's going to tell me what my a value is. So looking inside here, I don't see k over n. That would be k delta x if I just had 1k over n. I see 3k over n. So that means that my delta x inside here is actually being multiplied by 3. So I'm going to rewrite this Riemann sum as follows. So everything is going to be exactly the same, except I'm going to write 3 parentheses k over n. And this k over n in here that I've kind of isolated, this is my delta x. This is my k delta x. So now I'm going to try to convert this into my integral form, integral from a to b of f of x dx. Again, the 1 over n, that's your dx. But now I have to pick out my a and my b value and my function. So let's pick out the lower limit of integration. To get that, I have to figure out what is being added to my k delta x. Well, here's my k delta x. What is being added to this before stuff starts happening to that glop of stuff? Nothing. Nothing is being added to k over n before it gets multiplied by 3. It's tempting to look at this 1 and say, hey, 1 must be the lower limit of integration, but the 1 is not being added until after my k delta x gets multiplied by 3. It's supposed to be, if this was the lower limit of integration, it would get added in here before this stuff got multiplied by 3. So for that reason, I'm going to say that my a value here is 0. Nothing is being added to k delta x before the function starts doing its thing. So then if a is 0, b is going to be 0 plus whatever's on top of my n here in my delta x. So 0 plus 1 gives me 1 for the b value. This is going to narrow it down to, well, let's see, just choice A, right? That's the only one that is going from 0 to 1. And if we think about this kn now, k over n, as my x, this is really just the square root of 1 plus 3x. So putting it all together, I have integral from 0 to 1 of radical 1 plus 3x dx. Choice A.
For this problem, we want to know for what b value the integral from 1 to b of x squared dx equals this summation. So the key here on these summations is looking at this number over n that's on the end here. This 2 over n is telling us that we have an interval length for the whole interval of 2. And the reason it's telling us this is because, this is basically a whole bunch of base times height rectangle areas being added together by this summation. Over here, this 2 over n, this is all the bases, each with a very small length of 2 over n, because you have an interval length of 2 and you're chopping that into n pieces. So that tells you the length, the base of each rectangle. Anyway, our interval length is 2, and our interval is starting at 1 according to our definite integral here, our limits of integration. So 1 plus 2 is going to give you the b value up here, which is going to be 3. So that's going to be choice B. For this calculator-based problem, f is this rational, radical, weird function up here, and we're told that f is increasing on the interval from 1 to 7. We could probably figure that out on our own, but they're saving us a little bit of time. So they're saying that R3 is the value of the right Riemann sum, the RAM approximation, the RAM approximation for the integral from 1 to 7, using 3 intervals of equal length. Which statement is true based off of this? So if you look at these different statements, there's really 2 different possible values that we could have for this R sub 3. So we're going to have to calculate what R sub 3 actually is using a right Riemann sum approximation. But also, they're talking about this being an over or underestimate for the true value of the integral. And that's something we actually don't need to do any number crunching to figure out. We can figure this out right away. The key fact that's going to let us figure this out and immediately narrow this down to 2 answer choices is the fact that they told us that f is increasing. And it is known that a right Riemann sum approximation is going to overestimate an increasing interval. So RAM is always going to be more than the true value when you have an increasing function. So that's going to be narrowing it down to, let's see here, choices B and D that are saying R sub 3 is an overestimate. So now it just comes down to the true value of R sub 3. To figure that out, we're now going to approximate this integral with a right Riemann sum. Each of these is going to be the base times the height. And for each rectangle, we have a choice between 2 heights, one calculated by plugging in the left endpoint, one calculated by plugging in the right endpoint. And we're always going to choose the right endpoint of each rectangle because this is a right Riemann sum. So for the first one, we're going to have a rectangle length of 2 because we have a total interval length of 6, and we're chopping it into 3 pieces. So each of these rectangle bases is 2. So 2 times, now the first rectangle has endpoints of 1 and 3. So we're going to do f of 3, the right endpoint, in order to get the height of this particular rectangle. After that, we're going to be adding the base of 2 times the height of f of 5, that's the next right endpoint. And then finally, 2 times f of 7. So this is something you have to do on the calculator. You could spend a very long time trying to do this without one. So let's go ahead and do that now. So here I am on the calculator, and the very first important task that I've done is to take this function and put it in for y1, so I don't have to ever write it again. Let me quit out of there now. And to do this efficiently, I noticed that each of these terms here, these products, has 2 as one of the factors. So I'm basically going to factor out that 2, and in the parentheses, I'm just going to add together all of these f of kind of things. So to do that, I'm going to do alpha trace, pull up y1, and I'm going to open a parentheses and plug in 3, close the parentheses, then I'll do that same exact process again, alpha trace y1, and I'll plug in 5. This is f of 5 I just did, and then we do one more alpha trace here, y1, plug in 7, and close the other parentheses, press enter. Comes out to 13.133, which, again, that's going to be an over-approximation because this is RAM on an increasing interval. So that ends up being, let's see, choice D. For this problem, we have a continuous function f known to be increasing for all x's, and some values of f are given in this table here. L is the left Riemann sum approximation for the integral from 1 to 10 of this thing. We're using 4 subintervals indicated by the table. We want to know which statement's true. So each of these statements, we're talking about the value of this left Riemann sum approximation. We have 2 choices. It's either 1.8 or 2.8, so if you get a different number, you're wrong. And also over here, they're talking about whether this is an under or overestimate. So they've actually done us a huge favor here because we can figure out the over versus under thing right away based off of what the problem has given us without really doing any work. They told us that this was an increasing function. Well, we know that LRAM is going to underestimate increasing functions. You're always under the curve as your function increases. So because LRAM is under for increasing functions, that means we're going to have to pick an answer choice that says underestimate. So either A or C. So really, it's just down to the value of the left Riemann sum approximation. Okay, let's go ahead and set that up. So we can say that this approximation is going to be approximately equal to the following. So we have 4 rectangles. The first rectangle goes from 1 to 3, so that is a base of 2. And we have a choice of heights. We either do the negative 0.2 or negative 0.1. Since this is a left Riemann approximation, we always pick the left choice here between these 2 heights for each rectangle. So we're going to go with a base of 2 times a height of negative 0.2. And then for the next rectangle, that's going from 3 to 4, so that's a base of 1, times the left height of negative 0.1. And then the next base is 4 times our left height of 0.5. Actually 3, from 4 to 7 is 3. And then our next height is going to be 3 again, from 7 to 10, times our left height of 0.6. And all of these we have to actually add together because this is not what one of the answer choices is. So just doing this mentally here, we've got, let's see, this is negative 0.4 plus negative 0.1 is going to be negative 0.5. This is 1.5 over here, plus the negative 0.5, we're down to 1. And 1 plus, this is 1.8, that's going to come out to a grand total of 2.8, which is going to give us answer choice C, 2.8 and underestimate. On this problem, we're asking which of these Riemann sum limits here is equal to this integral. So the general setup for this is we're turning a definite integral into an infinite limit. Limit as n approaches infinity of the summation from 1 to n of, and in general we have f of x sub k times delta x. So we need to figure out these 2 items here and match it with one of these options over here. So let's deal with the delta x first, because we need to know the delta x in order to know what the stuff inside this f of x sub k looks like. So delta x, that is going to be the distance between your lower and upper limits of integration divided by the number of terms. It's basically your rectangle base on all these infinite number of rectangles that you're taking areas of and adding together. So we have a distance, an interval distance of 2, 3 minus 1 is 2, and we're going to divide that by n to get 2 over n. So that's our delta x. Already that eliminates 2 of the answer choices. We're down to choices B and D, where we have this 2 over n in the place of the delta x. So in order to get the rest of this, the f of x sub k, well, we need to figure out what x looks like. We have to find a way of representing all the possible rectangle heights, but for that we need to know all the possible rectangle x values. To get that, to get the x sub I, we're going to take the beginning limit of integration and we're going to add k times the delta x. And the k is just going to be a number that keeps going up as this summation keeps increasing the k number here, and it steps us through all the different rectangles. So we've got an a value of 1, that was our lower limit of integration, plus this is going to be k times 2 over n, that was our delta x, so 2k over n, and this is what x sub I looks like. So what does f look like? Well, looking up here, f is whatever's happening to the x in the integral. So it looks like we're cubing this thing, adding 2, and then taking the sign just for good measure. So that's all that stuff has to happen to 1 plus 2k over n. We have to cube it, add 2 to it, and then take the sign of all of that. So that's what the f of x sub k is going to look like in the summation. Don't forget we also have this 2 over n out here for the delta x. And then which answer choice does that match up with? It looks like going to be choice D. For this problem, we're given a summation form of an integral and being asked to turn it into the definite integral form. So we need to take this and put it basically in integral from a to b of f of x dx format. So let's start by picking out the limits of integration. So the a value is generally whatever is being added to the something times k over n term in here. In this case, that's 2. So we're starting with an a value of 2. This is our left endpoint. And to figure out the b value, we need to figure out the length of the interval. Well, that's going to be this 3 up here. Whatever's being divided by this n, splitting it into a whole bunch of infinitely small rectangles, this number up here tells us the length of the whole interval. So if we're starting at 2, and we have an interval length of 3, 2 plus 3 gives us a b value of 5. So we have an integral from 2 to 5 of something. Well, what's the something? What is this f of x actually going to be? So f of x is whatever's happening to the a plus k delta x term. In this case, here's a plus k delta x right here. What's happening to this whole thing? All that's happening is it's being fourth rooted. So this is just going to be the fourth root of x, and this 3 over n, this is really the delta x from summation form. That corresponds with this dx right here. So at the end of the day then, it's going to be choice B. For this problem, we're given an integral, and we want to turn it into a right Riemann sum, which is going to be one of these summations here. So in general, we're going from definite integral form to the form of limit as n approaches infinity of summation from k equals 1 to n of f of x sub k delta x, all this stuff. So we need to figure out the f of x sub k and also what the delta x looks like. And it's going to look something like this. Well, it's usually easiest to figure out the delta x because that's going to be the integral length divided by this infinite n value here. So going from 3 to 8, we have an interval length of 5. So our delta x is going to be 5 over n. And then to figure out this x sub k thing that we're going to plug into f, this is generally going to be the a value, the lower limit of integration, plus k times delta x. So this setup here. Our a value in this case is 3. And to that we're going to add k times this 5 over n term that we just found. So that's going to be 5k over n. So this is what x sub I or x sub k is looking like. Okay. So what's happening to this thing in this function up here? Well, it looks like we're taking the square root of 1 plus all of this. So when I write out my limit of my summation form here, I've got all this infinite stuff in the beginning. Now I'm going to have the square root of 1 plus parentheses 3 plus 5k over n. And this dx is being replaced by my delta x, which is going to be, again, 5 over n. This does not match any of the answer choices. However, they did something a little bit sneaky. If you look, you see some of these answer choices have a 4 in them. Well, where's that 4 coming from? Oh, we've got 1 plus 3, which is 4. So if we simplify this just a teensy little bit, we have 4 plus 5k over n. We have a 5 over n. And that is going to match answer choice D.